Hi everyone. In this video, I'm going to talk about the balls and bins problem, which is a very important problem in probability, and I will talk about how it is related to computer science. Once I have talked about the balls and bins problem, I will then talk about the coupon collectors problem, which is it's a very popular problem and is related to balls and bins. You might be thinking how a balls and bins problem is related to computer science. Balls and bins, this approach is very useful to model a whole bunch of different things in computer science. So let's first understand the setting, and then I'll give you an example of how this setting is used to model a real world computer science problem. So let's consider a process in which we randomly toss identical balls into B bins. So there are B bins numbered 1, 2, all the way up to B, and you're tossing these balls randomly. Now all these balls are identical, and as each and every one of these tosses is independent of one another, each ball is equally likely to end up in any bin. This is the process. So think about it. You have B bins in front of you and you pick up a ball and just toss it. It could just fall in any one of those bins. Now, how is this setting useful in computer science? You can think of these B bins to be B servers which are available for some company. Now, each ball that is being tossed can be compared to a user who is coming into the system. So, for example, let us consider a company, for example, Amazon.com. They have B servers, and each user or each ball that you're throwing is equivalent to a request that comes from a user, and it randomly goes to one of these B bins. So, that is the situation here. Now, as you're tossing a ball and it's equally likely to land up in any bin, the probability that a tossed ball lands in a given bin, say you're considering one particular bin, is 1 over b, because it can land in any one of those b bins with equal probability. Now, this ball tossing sequence is a series of Bernoulli trials. Because each trial is independent of one another, that's a Bernoulli trial, and the probability of a ball landing in a particular bin, say a particular bin of your choice, is 1 over b, and that can be looked upon as a probability of success for that bin. Okay, so now that we have understood this particular setting, let's consider the first problem, or this first question, which is how many balls fall in a given bin. Now, to answer this question, let us first try to understand how we can model this problem. Now, number of balls falling in a given bin can be modeled as a binomial distribution. So this follows a, a binomial distribution. How is that? This is because what you have is each throw of a ball is a Bernoulli trial, and what we are having is, say you are tossing n such balls, and you're interested in finding the probability of k balls landing in a particular bin. Okay, so this is n tosses, and the distribution of k balls is what we are interested in landing in a particular bin. So how do we go about writing that? In n tosses, the distribution of k balls landing in a bin, it can be given by n, choose k, 1 minus b to the power of n minus k, b 1 by b to the power of k. Okay, and why is this the case? Because you are tossing k balls and you want those k balls to land in a particular bin. The probability of those k balls landing in a bin of your choice is 1 over b for each of those balls. So you have 1 over b raised to the power of k. Now the remaining n minus k balls you can land in any one of the other bins, and that probability is 1 minus 1 over b. So that's the probability of a failure. The ball landing in the bin of your choice is the probability of your success. Okay, so 1 by b raised to the power of k, and 1 minus b raised to the power of n minus k. And we can choose any of these k balls that you're tossing out of the n balls that you're tossing, and therefore we have n choose k. So this follows a binomial distribution. So you see, this balls and bins problem, what we have is we can pose this question, and this question, the answer to this question is the binomial distribution that we've studied in the earlier video. Okay, so now let's try to answer another question, which is how many balls must we toss until a given bin contains a ball? So how do we answer this question? So you're tossing these balls, and say you're interested in a ball falling in a particular bin, say bin number 5, and you toss the first ball, it lands in some other bin. You toss the second ball, it lands in some other bin. Toss the third ball, it say lands in bin 5, the bin that you're interested in. Now, next time you repeat this experiment, maybe you take 5 tosses till it lands in your bin 5. The next time you repeat, maybe the second attempt itself, the ball lands in bin 5. So the question is, how do you find this distribution? Now, if you model this problem carefully, you will see that the number of tosses until a given bin receives a ball follows a geometric distribution. Okay, and why is this the case? Okay, so a ball falling in the bin of your choice is a success. Now, the number of attempts that you make before that which have ended in a failure. Okay, so it is basically you toss a whole bunch of balls till you get a success, which is the ball landing in the bin of your choice. So bunch of failures followed by a success, which is nothing but a geometric distribution. Therefore, if you assume that the number of tosses is denoted by the random variable x, then probability of x equals k, that is essentially success on kth attempt is equal to 1 minus 1 over b to the power k minus 1 by b, which is the success. So k minus 1 failures followed by a success. So the answering this question turns out to be nothing but a geometric distribution. Now you see the balls and bins setting renders itself beautifully to a whole bunch of different distributions that we have studied and helps us answer these different kinds of questions. Now, having done that, now let's look at the next question, which is how many balls must we toss until every bin contains at least one ball? Okay, so this is a pretty challenging question. So let's first try to understand this. So you first toss a ball. The first toss will definitely land in one of the bins. Now, when you toss the second ball, it could land in the bin that the first ball landed, or it could land in some other bin. Now, as you keep tossing more and more balls, more and more bins will start containing balls. Now, at some point when you toss a ball, the final empty bin will also contain the ball. So you have to toss a whole bunch of balls because you don't know where the ball is going to land. Maybe it lands in a bin that already has a ball. So you have to keep repeating this process. One thing that you can understand is initially it is easy to fill the bins because there are a whole bunch of empty bins which don't have a ball. But as you toss more and more balls, more and more bins get filled up, and hence after a certain stage it is hard to find that bin which does not have a ball. Okay, so we have to first understand how we want to solve this question. Okay, to do that, let's consider, model this problem this way. When a ball falls into an empty bin, we call it a hit. Okay, this is what we call as a hit. Okay, now the question is, how many balls must we toss until every bin contains at least one ball? Okay, so this is not a very concrete question. So let's just try to find the expectation. Okay, so we want to know expected number of tosses till we get B hits. Now, recall that a hit is when a ball falls into an empty bin. So if you toss a ball and it falls into a bin which already has a ball, that's not a hit, that's a miss. Okay, so we will first want to get B hits. When we get B hits, that means that every bin contains at least one ball. Now, this particular problem that we are going to solve here, this is the coupon collector's problem. Okay, and I'll describe later why it is called so. Okay, so at this stage, to solve this question, what we are going to do is this. We're going to partition the n tosses into stages. So we partition the n tosses into stages. That's what we are going to do. Now, the ith stage. Okay. Now let's define what the ith stage is. The ith stage consists of the tosses after the I minus 1th hit and until the ith hit. Okay, so what is this? So we're going to partition the n tosses into stages. So the ith stage consists of tosses between the I minus 1th hit and the ith hit. So you don't know how many tosses you would take to get the ith hit. Maybe it will take only a single toss. You toss the ball and it falls into an empty bin, so you get a hit. Maybe you can take 2 tosses, maybe you take 3. And in the worst case, you can take up to infinity. Okay, so that is the understanding that we are going to develop here. Okay, so we are going to model the ith stage. Okay, and then we are going to add up all these stages going from I equals 1 to B. Okay, because they're going to be B such stages. Okay, so let's try to model the ith stage. Okay, so for each toss in the ith stage, so we are looking at the ith stage. So for each toss in the ith stage, what do we have? We have I minus 1 bins that are empty. So for each toss, when you're doing the ith stage would end if you get a hit. So when you're tossing a ball in the ith stage, I minus 1 bins are actually empty. So how can you model this? What you can see that for each toss in this stage, the probability of getting a hit, so we're looking at the ith stage, so the probability of getting a hit is B minus I plus 1 by B. How do we get B minus I plus 1? Basically, B minus I plus 1 is gotten by B minus I minus 1. Okay? So their number of empty bins at this stage is B minus I minus 1. okay, like this. So these are the number of empty bins, b minus I minus 1. Okay, empty bins at this stage. So if the toss that you do for this ball lands in one of these empty bins, then what you have is you are going to get a hit. Otherwise, you're going to get a miss. Okay. Now, one thing to note is for stage 1, for the first stage, you are guaranteed a hit. Because every bin is empty when you're tossing the first ball, and at that time it will fall in one of those bins. So you're guaranteed a hit. Okay. Now we have gotten this. Now what you can understand by this, like for the ith stage, we are going to model it, and this model is going to turn out to be a geometric distribution. So let Ni be the number of tosses in the ith stage. Now Ni is a random variable because you don't know how many tosses are going to be needed. So it is a random variable, that much is sure, and therefore it is going to have a geometric, going to have a distribution. Its distribution is going to be a geometric distribution. Why is that? Because when you toss, and the probability of getting a hit is b minus I plus 1 by b. Okay, so each Ni follows a geometric distribution. Follows a geometric distribution, and the probability of success is 1b minus I plus 1. It's 1 divided by b. So this is the probability of success here. Okay. So what have we done? So far we have looked at the ith stage, and we have tried to model the number of tosses that you need in the ith stage. Now n be total number of tosses. So n is the total number of tosses that you need. Therefore n is nothing but summation I going from 1 to b in I, because there are b stages, because Ni is the number of tosses that you need in the ith stage, and there are going to be b such stages starting from the first hit all the way to the bth hit. Now what we need to find here, we are trying to find the expected number of tosses that are needed. So n itself is a random variable which is a summation of these b random variables, n1, n2 all the way up to n subscript b. So expectation of n is going to be expectation of I equals 1 to be Ni. And this expectation can be pushed through this summation, and therefore we will have I equals 1 to be expectation of Ni. Okay. Now Ni is a geometric random variable. Okay, because it's a geometric random variable with success, probability of success is b minus I plus 1 divided by b. The expectation of Ni is going to be 1 over the probability of success. Because it's 1 over the probability of success, it is nothing but b by b minus I plus 1. So that's the expectation of Ni. Okay. Therefore, we have expectation of n coming out to be summation of I running from 1 to b divided by b minus I plus 1. Okay. So what we can do here is B is a constant, so it can come out of this summation. So we have B over 1 by B minus I plus 1. Okay. Now I is going to run from 1 to n, 1 to b. Now when I takes the value of 1, this fraction 1 by b minus I plus 1 will take the value of 1 by b. When I takes the value of b, it is going to take the value 1 by b minus b plus 1, which is going to be 1 by 1. So we can rewrite this as b times summation I running from 1 to b 1 over I. Because essentially the summation is adding numbers like 1 by 1 plus I plus 1 by 1 plus 2 all the way to 1 by 1 plus b. And that's the same thing that we achieve if we write it in this form. Now if you write it in that form, and if you have a large number of bins, you can write it approximated by b ln b plus O of 1, where O of 1 is a constant, and we are not trying to find the exact expression. I am just trying to give you an algorithmic bound, because that is the expression and we want to evaluate it. This is how it will evaluate to, and this can be solved as O of b ln b. Now as b grows larger and larger, expectation of n is going to be O of b ln b. Okay. Now this problem is called the coupon collectors problem. Okay, and why is this called so? So you can say that a person is trying to collect b different coupons. So that's what the person is trying to collect. So the person is trying to collect b different coupons, which correspond to the b bins here. Okay, and the question that we are trying to ask is how many total coupons he will need to acquire. So to collect these b different coupons on expectation, he needs to acquire O of b ln b coupons. Okay, so this is the coupon collectors problem. Okay, I know that this problem is pretty intense and challenging. Therefore, if you cannot understand this concept, I encourage you to go over the video once more. But this is a very important problem and it's very useful in computer science. Thank you for watching, and if you like this video, do subscribe to my channel.